Alright, so here's my metal bar, metal wire. So metal on metal is a complete circuit conductor. So right now this is a complete circuit. Is there a battery? Is there current flowing through it? No battery, no current, just sitting there. So if I take an external magnetic field, so maybe a magnetic field created by a bar magnet or some other source, but not these wires. So that's what external means. It's created by something that's not in the picture. So these are my external magnetic field lines. They're directed into the page because I love into the page X's. They're easier to draw than dots. And if I were to take this bar and move it, but I didn't do a good job of making it a whole bar. So if I take this bar and I were to move it over here, what's going to happen to the area? So imagine our bar is over here now. What's happening to the area of this loop? Did it increase, decrease, or stay the same? I moved the bar. It's no longer here, but it's there. What happens to the area of this loop? Okay, so our area is decreasing. So we have a change in area. Well, let's look at what else we could measure. Well, maybe the bar has a length L, and it moves along here a distance of, we'll call it delta D. So by how much does the area change? L delta D. That's right. Okay, so we've got an area change. This bar, if it's moving, it probably has a velocity. Maybe like that. And if our induced EMF, if our induced EMF is B delta A, the angle between the magnetic field and the normal to that loop is 0, so the cosine of 0 is 1, divided by delta T. Substitute into your area, you're going to have B L delta D over delta T. Does anybody know what delta D over delta T is? It's the velocity of that bar. So that would be what? BLV? We call that the motional EMF. The EMF is equal to BLV. Motional EMF.